Welcome to the visit training session titled Utilizing Synthetic Imagery from the NSSL 4-Kilometer WRF ARW Model in Forecasting Low Clouds and Fog. My name is Dan Bicus. Dan Lindsay and myself put this together, and you can see the other folks listed down here at the bottom as well. This training session is part of a series that focuses on applications of synthetic imagery from the NSSL 4-Kilometer WRF ARW Model. In this training session, we'll consider applications of the synthetic fog product towards analyzing low clouds and fog. The primary motivation for looking at synthetic imagery is that you can see many processes in an integrated way compared with looking at numerous model fields and integrating them mentally. What are our learning objectives? Well, we want to learn to apply cloud cover forecast from the NISL WRF ARW synthetic low cloud and fog product. This is an efficient visual comparison between model output and the GOES Heritage Low Cloud and Fog product. This can discriminate between low-level and high-level clouds displayed in a way that's similar to the GOES Heritage Low Cloud product and Fog product. The only big difference is that we're looking at forecast output from a model rather than an analysis, which is what this GOES Heritage Low Cloud Fog product is. And also we want to be aware of limitations, including reflected solar radiation is neglected, and this is a limitation in that comparison between the synthetic fog product and the GOES Heritage Low Cloud and Fog product is only valid at night. However, there's other products to compare the synthetic imagery with that we'll discuss here. Other limitations include a false cloud signature. You'll see this over the southwest U.S. This is due to surface emissivities at the same wavelengths. Also, it does not discriminate between low clouds and fog. Synthetic imagery is model output that is displayed as though it is satellite imagery. Analyzing synthetic imagery has an advantage over model output fields, such as relative humidity, in that the feature of interest appears similar to the way it would appear in satellite imagery. There are multiple sources of synthetic imagery available on the web. For example, the CRAS model at the University of Wisconsin has been available for some time. The primary focus of this training session is from the NSSL 4-Kilometer WRF ARW model. The model is run once a day at 0Z. Certain model output fields are distributed to CIRNA and SIMS. These model fields are used as inputs into a model that generates the synthetic imagery. Gaseous absorption is calculated for cloud-free points, and modified diffraction theory is used to obtain scattering and absorption by the cloud particles. The model outputs brightness temperatures for a number of satellite bands. For more information on the details of synthetic imagery generation, refer to the references on the Student Guide webpage. The GOES Heritage Low Cloud and Fog product is based on the fact that liquid water clouds have an emissivity at 3.9 microns, that is less than that at 10.7 microns, thereby making the fog product show a positive difference. One key difference between this product and the GOES Heritage Low Cloud and Fog product is that the reflected solar radiation is neglected in the synthetic imagery due to computational limitations. That is, the synthetic imagery is assuming nighttime is constant. In the GOES Heritage Low Cloud and Fog product, you will notice the brightness temperature difference of low cloud and fog transition from positive to negative between nighttime and daytime. In the synthetic imagery, the difference will remain positive due to the assumption of zero reflected solar radiation. Hourly output is generated for the 9 to 36 hour forecast, valid 9Z of day 1 to 12Z of day 2. Once the new model run comes in, it writes over the 33 to 36 hour forecast, valid between 9 and 12Z from the previous run. The bands are those that will appear on GOES-R, since the project is based on demonstrating products that will be available on the GOES-R satellite, scheduled for launch around 2015. The bands are very close to those found on the current GOES satellite, as you can see here, so that the principles discussed in this training session readily apply to operational GOES satellites of the present. Here's the synthetic low cloud and fog product for 27 January 2012. This is from the 0Z 27 January model run. It's easy to discriminate between high-level clouds and low-level clouds because high-level clouds show up as black and dark gray. For example, here in the Central Plains, we see some high clouds moving over California, and then over here in Florida. And then the low-level clouds are these blue colors. So we have increasing positive difference from light blue to darker blue, as you can see, which would give increased confidence in low-level clouds. We can see that across the southeast and going up into the Ohio Valley region here pretty easily. Remember that we cannot discriminate between low clouds and fog from this product alone. Other data sets must be examined to address this. Note the regions that appear to be low cloud in the southwest U.S. I'll point out some regions here in the northern Mexico region, far west Texas into New Mexico, and also right around the Four Corners. Notice that they are there for the entire duration of the loop and do not move. This is a false cloud signature that is a consequence of surface emissivities at the two channels. The easiest way to spot the false cloud signature is to look at the loop, and the areas that don't move at all throughout the duration of the loop are likely false emissivity signatures. Also, these signatures tend to show up in the southwest U.S. and Mexico. Across Louisiana, Mississippi, and Arkansas, we see the development of the low cloud signature during the nighttime hours. And next, what we're going to do is investigate this by further zooming into the region. Before we do that, I just want to point out a few other things. You may notice the odd streaks in the Pacific Ocean off the west coast out here. Let's go ahead and draw some of these in here. This is due to the way that the data is processed in AWIPS. You will not see this in the product on the SIRA web pages. This artifact in AWIPS leads to a plus or minus 0.5 degree uncertainty in the difference product. However, by utilizing the advised color table, this artifact will not have a meaningful effect on the interpretation of the location of low clouds and fog. As I said we would do in the previous slide, we're zoomed in now over Arkansas, Louisiana, and Mississippi, and the reason is we see some areas where it appears we have this low cloud signature developing during the overnight hours, and that could be due to fog, and that's something that we're going to look at here more closely. So we're looking at the synthetic low cloud and fog product between 9 and 17Z on the 27th of January 2012. In the eastern half of the scene, we see low clouds advecting towards the east and southeast. In the western half of the scene, we see the development of low clouds during the nighttime hours. These clouds appear to expand and then dissipate more than advect like we see further to the east here. So we may suspect radiation fog development in the western portions here, across Louisiana, Mississippi, and Arkansas. We'll look at other data sets to confirm if this is indeed radiation fog. Here's the GOES fog product over the same time period with observations overlaid. We're also using the same color table. The METARs show a small temperature dew point spread and light winds, which would support radiation fog development. The fog product shows the development of low cloud regions in the same general area as the synthetic fog product, and it appears to be a radiation fog rather than an advective fog, while the METARs provide confirmation of fog, particularly here across portions of Mississippi that I'll go ahead and draw in. Note that we see a transition from a positive temperature difference, which is blue, to a negative temperature difference, which is this dark gray and black, as the sun is rising. So note the times here. We see that transition particularly here across Mississippi. This makes sense since we're introducing a solar reflected component, which is detected in the 3.9 micron channel. This will not show up in the synthetic imagery because nighttime is assumed to be constant, therefore no solar reflected component. By the end of the loop, we see dissipation of the fog region in Mississippi over here, but it's complicated to some extent with the transition between a positive temperature difference and a negative temperature difference, and then by the very end of the loop, it goes away. One way to get around this change in temperature difference between nighttime and daytime is to utilize the CIRA low cloud and fog product. This allows the user to observe low cloud or fog the same color regardless of time of day. In this enhancement, low cloud or fog is light gray to white, while high-level clouds are color enhanced like the usual IR imagery. Note that the fog and low clouds stays the same color here in that transition between nighttime and daytime. So that is the advantage of using this product here. We'll end this case with the familiar GOES visible imagery starting from sunrise up to the time from the previous loop. The dissipation of the fog in Mississippi can readily be seen here in the visible imagery. For our next example, we'll look at the synthetic low cloud and fog product from the November 30th, 2011 case. The area of interest is the Central Valley of California. Remember to neglect the false cloud signature that we see throughout portions of the west. I'll go ahead and highlight here in particular regions. Midway through the loop, we spot low cloud or fog in the Central Valley of California. I'll go ahead and circle that. And it dissipates from north to south in time. Here's the CIRA low cloud and fog product, which shows the low cloud and fog signature over the Central Valley of California, dissipating from north to south. Here's the GOES visible imagery showing the low cloud and fog signature. The biggest question you may have is, why does the aerial coverage of the low cloud and fog appear much larger than what was forecast in the synthetic imagery? This may be a result of inadequate vertical grid spacing in the model in a situation with a very shallow layer of fog. We've seen this trend in other cases as well, so it's just something to look for and anticipate. Moving on to the next case, here's the synthetic low cloud and fog product between 0Z and 15Z, 19 March 2012. Since the time spans across 9Z, we introduce a new model run between 8 and 9Z, so that the 0Z through 8Z images are from the 0Z 18 March model run, and from 9Z on, we're looking at the 0Z 19 March model run. Up to 8Z, the trend appears to be the advection of low clouds from the Atlantic westward towards the coastline. With the new model run, we see extensive low cloud development from eastern North Carolina northward to Pennsylvania. We'll analyze the GOES Heritage Low Cloud and Fog product only during the nighttime hours and end the loop before sunrise. Although the coverage of low cloud is less than the model forecast, we can see localized areas of low cloud development from eastern North Carolina and around here to eastern portions of Virginia to the Delmarva Peninsula around here, and also the northern portions of Chesapeake Bay. Now we can overlay the METARs here to identify what areas have fog, and you can see, we go ahead and look more closely here, down here in southeast Maryland, and then it looks like in the northern end of Chesapeake Bay in particular here. In the GOES IR imagery, this is the 10.7 micron channel. It is more difficult to identify the regions of low-level cloud that we just identified in the GOES fog product. Perhaps the best use here is to identify some areas where higher-level clouds are advecting over areas where low-level clouds exist. The CIRA low cloud and fog product, along with the METARs, highlight areas of low cloud and fog. Remember, in this particular enhancement, these are lighter shades of gray or white. For example, the eastern coast of North Carolina, southeast coast of Virginia, the coast of Maryland, and the northern Chesapeake Bay around Baltimore into southeast Pennsylvania depict the areas of low clouds and fog. Near the end of the loop, you can see some areas where the low cloud and fog is dissipating. Here's the SIMS GOES-R fog and low stratus product. This is an analysis product that shows the probability of IFR conditions expressed as a percent. Ideally, the synthetic imagery would be used to see where fog may occur for the future, and this product would show if the forecast is verifying. It does have an advantage over the CIRA low cloud and fog product, as well as the GOES Heritage low cloud and fog product, for example, in that it is a fused product. That means it makes use of satellite imagery as well as very short-term NWP output, so that it can discriminate between fog and low cloud, and also multi-layered cloud decks are not an issue. In this particular example, we can see maximum values around the Chesapeake Bay in this region, and particularly in the northern part of Chesapeake Bay. And the maximum values peak right around 10:15 UTC, times indicated down here, and it decreases significantly by about 14:15 UTC. This is quite similar to what was forecast by the model that was shown in the synthetic imagery that we just looked at. The synthetic imagery can be very useful on days that you're expecting convection, and one of the forecast questions is how much insolation will take place for sufficient instability to develop. In the synthetic IR imagery, we see low clouds forecast during the morning hours over portions of the plains from Texas to Nebraska. These clouds are forecast to dissipate over a large portion of the region, with the exception of further north in eastern Nebraska and also into parts of Kansas. Convection is forecast to develop along a boundary that becomes apparent by 22Z, pretty much across this region right here. Here's the synthetic low cloud and fog product for the same period of time. The thing to note is how much easier it is to identify the low-level clouds of interest. The low-level clouds are easier to identify and discriminate between the higher-level clouds, for example, out here in these dark or black colors, and also the ground. The color table helps identify the low-level cloud as it stands out being colored blue. The only disadvantage to mention is that we do have regions of false cloud signature here in far west Texas and into New Mexico. That's a consequence of the emissivities of the two channels as we discussed earlier. Here's a comparison between the synthetic low cloud and fog product and GOES visible imagery at 14Z. And what I'll do is fade in between the two. And by doing this, we can see areas where you can see the model is doing well in terms of the low-level cloud coverage. For example, here in North Texas up into central Oklahoma, maybe not so well here in far west Texas, but it seems to be doing pretty well here in the eastern half of Kansas, maybe not quite so well out here, and then also appears to be doing pretty well in Nebraska. So it gives you a quick look here at comparing between the model forecast and the observed imagery, and this should give you more or less confidence in terms of the model forecast for that time period, and as you go forward during the day, you can continue to make this comparison to gauge how much confidence you can have in the model forecast. Here's the GOES IR imagery, the 10.7 micron imagery, to see what took place. Most of the low cloud dissipation that took place over Texas, Oklahoma, and Kansas was well forecast, allowing sufficient insulation to take place in the warm sector ahead of the dry line where convection developed late in the day. Note the region of clouds in southeast Nebraska, right here, where they appear to be breaking up to some extent by afternoon to allow for some insulation to occur. We see convection develop in southeast Nebraska by the end of the day. The GOES visible imagery during the same time period offers the best resolution data possible at 1 kilometer versus that of 4 kilometer in the IR that we were just looking at, which is important for regions like southeast Nebraska. In the IR imagery, it appears to have some clear breaks within a field of low-level clouds by late afternoon. The visible imagery, with its higher resolution, shows considerably more clearing than looking at the IR imagery. Keep in mind that this difference in resolution may show up in the synthetic imagery as well. The synthetic imagery is at 4 kilometer resolution, so that a field of partly cloudy skies may be smoothed out at a 4 kilometer resolution and appear to be a greater cloud coverage than reality. And this particular case shows that pretty nicely here across southeast Nebraska, where it's actually quite a bit more clearing in the visible imagery than you would have suspected from the GOES IR imagery or the synthetic low cloud and fog product. In conclusion, the synthetic low cloud and fog product provides forecast cloud information and discriminates between high and low-level clouds that are forecast by the model. It's displayed in a way that's similar to the GOES Heritage low cloud and fog product. This makes for an efficient visual comparison between model output and the GOES imagery. It does not discriminate between low cloud and fog. That's an important thing to keep in mind. Another limitation is that the false cloud signature that you'll see over the southwest U.S. Again, this is due to surface emissivities at the same wavelengths. Another limitation is that radiative fog events may be underdone, and that's due to most likely inadequate vertical grid spacing in the model. Important thing to remember is that the synthetic imagery is a forecast product. So ideally, you would use the synthetic imagery to see where fog might occur in the future, and then use the evolution of an analysis product to see that the forecast is verifying. And the recommended analysis product here is the SIMS GOES-R Fog Low Stratus product. And you can refer to the Visit Web Pages training session on the GOES-R FLS product, as it's referred to, for more information on that particular product and also how to receive that in your AWIPS. Where to view the synthetic imagery? The synthetic imagery is part of the suite of GOES-R Proving Ground products that is made available in AWIPS via an LDM. And for those offices that are currently receiving it, they have been providing us feedback, and that's valuable for the developers in terms of improving products and getting ideas for future products as well. If you'd like to view this online on the web pages, here's the CIRA website. If you'd like to look at individual model output fields from this particular model, that's available right here. And using an appropriate color table is extremely important for this particular product. So to obtain the color table that we showed throughout this training session here, you can go ahead and download that file right here, and then refer to the SIM Fog enhancement that you'll see when you load up that particular set of color tables from here. And finally, here's our contact information. If you have any questions or comments, feel free to email myself. If you have